Hey Calc AB, this is a video about alternative ways that the AP has talked about volume. So I just wanted you to watch it before the AP test. So this is a picture of a pool, and you can see that the pool has different depths depending on where you are in the pool. And in general, if you think of a pool as a rectangular prism, just like a big box, the volume of this box would be length times width times height. And so you'd have to collect a bunch of these boxes with differing heights depending on where you are in the pool. So we're going to look at a few problems. And the first few are about a pool. So number one, a rectangular pool is 20 feet wide by 15 feet long. The empty pool fills up with water at a rate of 2 feet per hour. Find the volume of water after 4 hours. So these values are constant, but what's changing is the height of the water because of the rate of the water filling up the pool. So if the rate is 2 feet per hour, the height of the water or the depth of the water is going to be 8 feet. So then you can multiply to find the volume. Length times width times height, so 20 times 15 times 8 is 2,400, and the unit should be feet cubed. In general, volume is going to be a cubic measurement. Number two, a rectangular pool is 18 feet wide by 24 feet long. The table below shows the depth h of the water at 3-foot intervals from one end of the pool to the other. Estimate the volume of water in the pool using 8 equal subintervals of length 3 with, and then you have all different depths for the pool. So one thing that they've done is they've taken the length of the pool, which is the 24 feet, and they've divided it into these 8 subintervals. So what's constant in this question is the 18 feet wide. That's not changing, but the depth over these different subintervals over the 24 feet is different. So like for this first interval, if we're going to use LRAM, we're going to take 3 feet for depth. And then for this interval, we're going to take 2.1 and so on all the way down. So you can look at the LRAM calculation. So the volume is going to be length times width times height. The width is the 18 feet. The length is broken down into these 3-foot intervals, and each of those intervals has these different values for the depth of water. So realize that you really do have 3 dimensions here, and so you get this volume calculation. To take the RRAM, you'll work from right to left. So for this interval, you use the 10 feet of depth. For this interval, you use 8.1, and so on. But in general, it's still the same idea, that it's length times width times height, just depending on how you order those values. Number 3, you're responsible for stocking the town pond with fish before the fishing season. The average depth of the pond is 40 feet. You measure distances across the pond at 100-foot intervals. Give an estimate, including units, of the volume of the pond using LRAM and RRAM. So in this particular question, this one has the depth being held constant. And the different intervals have different distances across the pond. The other thing that's interesting about this question is that there are 100-foot intervals, but the table is only giving us the interval number. So that's why you see this 100 in our calculation. Because if you're trying to get how much volume there is, you need to make sure that the units work out. So we've got 40 feet of depth, 100-foot wide intervals, and then you have feet going across the pond. So that's going to give you feet times feet times feet, which is giving you a feet cubed calculation. The LRAM, you're going to take the leftmost points and you're going to cross off the rightmost one, and then switch it for RRAM. So you take the rightmost point, use all of these, and you cross off the leftmost point. Number 4, use the left endpoints of 6 equal subintervals to approximate the volume of a 12-foot long trench that runs from west to east with depths given by h, where x is the distance from the west end. The width of the trench is 4 feet. Include units in your answer. So in this question, the width is what is being held constant. So if you look at my calculation, I've got this 4. Right here we have 4 feet. And then we're taking the 12-foot trench. It's 12 feet long, and we're dividing it into the 6 subintervals. So if you look at my graph, I've got the 6 different points here, and I know that it's 6 because they're telling me so in the question. We're also going to use LRAM because of the word left, or the phrase left endpoints. And so 12 divided by 6 is giving me the 2. So each of our rectangles is going to be 2 units long. The last part of this is how do I get each of these values in parentheses. I'm going to use my calculator, so I'm going to put this function into y1. You have some choices. You can make a table. I think that's the fastest way. Remember to turn on the ask feature, and then you can type in 2. You'll want to type in 0, 2, 4, 6, 8, and 10 because you're using left endpoints. Or you could do, y1 of 0, y1 of 2 on your home screen, etc., all the way down to y1 of 10, and that'll give you these. So just like in all the other questions, you want to make sure that your units work out, that this is giving you a volume unit. You've got 4 feet wide, 2 foot long intervals, and then different depths that are each of these calculations. So that gives you feet cubed. It did say to include units in your answer, and so you should make sure you do that. Shame on me. This last section is about cross-sectional areas. And it's very similar to how we ended the school year with finding cross-sections of solids where we had squares and right isosceles, triangles, etc. It's just this time we don't know the shape. So just as a reminder, volume can be expressed as the integral of areas of cross-sections times their thickness. Remember that an integral is a sum, and this right here is just little itty-bitty volumes, and when you add those all up, you get a larger volume of a solid. So in our class, we jumped straight to the integral, but you can also be asked to do this with LRAM, RRAM, or MRAM. So if you look at the questions ahead, we want to estimate volumes of water on different intervals. So pay attention to the interval that they're giving. So we've got 0 to 2, 0.4 to 2.8, and 0 to 3.2. So because of that, you'll see different values being taken. So for letter A, we have 5 equal intervals on the interval from 0 to 2. So we're going to stop right here. We're using LRAM, and the width is 0.4 for every single one of these. And if you notice also that first row is in feet, and the areas of cross sections are in inches squared. So we want to make sure that our units are consistent. So we want to convert these feet into inches. So if you look down here in the calculation, that's just doing 12 times however wide or thick that interval is. So 12 times 0.4 gives us a unit of inches, and then we do LRAM for those 5 values. So we use these numbers, and we cross off this last one. The next question, part B, estimating the volume of water on 0.4 to 2.8. We're using this section of numbers. It is asking for RRAM, so we use these values, cross off this one, and every single one of these intervals is 0.4 thick. And there's our 6. Just in this example, likewise, we multiply by 12 to convert into inches, and then this represents inches squared. Letter C wants us to use MRAM over the entire interval, but this time you're taking it by midpoints. So for that reason, the width or thickness of each of our cross sections is going to be 0.8 wide. 0.8 feet wide, I should say. So multiply by 12, and that converts this unit into inches. Then the MRAM takes the midpoints of each of these intervals. So that's why we're using the 1.4, 2.0, 1.8, and 0.4 values. So your final unit should be inches cubed.